To understand how informational criteria for firing are set up in a given neuron, it's not enough to specify how input neurons are physically connected to that neuron. It is also necessary to model how synaptic weights on inputs to that cell change dynamically, effectively changing its neural epiconnectivity. In this section, I would like to describe a useful metaphor for what I think is going on with rapid synaptic reweighting as a basis for the neural code. In future sections, we will cover how top-down processing might harness such a neural code for the fulfillment of high-level aims like think of a European woman politician, or coming up with ideas in answer to the question, what should I make for dinner? But before moving on to top-down processing, and in particular, top-down volitional processing involving volitional attention, I would like to cement your understanding of what rapid synaptic reweighting might be like in the brain. We've covered AMPA and NMDA receptors, and later I'll argue that rapid synaptic reweighting involves the opening of just these ionotropic receptors. But for now, let's develop an intuition for rapid synaptic reweighting using a useful metaphor. A common assumption in neuroscience is that information processing in the brain is realized in action potentials, and that mental causation must be realized in a succession of action potentials triggering action potentials. Many people have thought that this process might be deterministic, like Newtonian billiard balls banging into each other and making each other move, except that now action potentials trigger action potentials. This is a fundamentally incorrect way to think about how action potentials coming from presynaptic neurons trigger an action potential in a postsynaptic neuron. The process is deeply non-Newtonian and profoundly non-linear. It is also not deterministic, but I'll argue in the next section, indeterministic. Nonetheless, action potentials triggering action potentials is no doubt part of the story of the neural code. You can think of it as the yang of the neural code, but there's also a yin of the neural code. Much recent evidence suggests that dynamic short-term changes in synaptic plasticity can also play the role of a neural basis for information processing. Many neuroscientists have thought that deciphering the neural code would mean deciphering the information carried by action potentials per se, as if a train of action potentials could be deciphered like, say, the Morse code or the Enigma code. But which inputs will make a neuron fire is dependent on the synaptic weights that are imposed on incoming presynaptic action potentials at a given moment. If information is physically realized when it is made explicit, and it is made explicit when a neuron fires and passes that information on to other neurons, then the information that a neuron will realize if it fires is implicit in its synaptic weights, even before the arrival of any presynaptic action potentials. Facts about action potentials in isolation of the inputs that trigger them will not carry information about anything. A given neuron might fire identically given one set of inputs at time 1 and a different set of inputs at time 2. Since different information would be realized, the information cannot be localized in action potentials per se. If you know that a neuron has fired, but you don't know what inputs made it fire, then you do not know what information has made it fire. But if you know that a neuron has fired given particular physical inputs, which will only occur when certain informational facts are the case, then you can know what information made it fire. As we discussed in the last section, using the example of a simple cell, if an action potential arriving at a synapse is multiplied by a synaptic weight of 0, it contributes nothing to the firing of the postsynaptic neuron, and therefore nothing to its information processing. Therefore, observing an action potential without knowing about how it is filtered by synaptic weighting cannot tell you what information it conveys, if any. So here's an analogy. How the mouth is formed determines whether the same vibrating air passing through the mouth will lead to the enunciation of, say, an ah, or an o, or an oo sound. For example, ah, o, oo. The mouth can be formed into an ah, or an o, or an oo shape before any air is forced through it, just as neurons can be criterially reset before being driven to fire by the arrival of action potential inputs from presynaptic neurons. The bit of information ah versus o versus oo does not exist in the vibrating air in isolation of the shape of the mouth through which it is filtered. Rather, this information comes into being as the vibrating air passes through either the O, A, or U mouth filters. On this account, action potentials are analogous to the vibrating air, and momentary synaptic weights are like filters that determine the information expressed by action potential input. The search for the neuronal code is likely to be more fruitful if the focus is on neuronal criterial resetting rather than on action potentials in isolation of synaptic recoding. Cracking this kind of criterial neural code poses a major challenge to neuroscience because, given present single and multi-unit neuron recording methods, action potentials are easy to observe, whereas dynamic synaptic resetting over thousands of synapses is not. At present, we don't really even have good methods to observe the dynamic weight of a single synapse, let alone how hundreds or thousands of them are dynamically changing in a single postsynaptic neuron. However, if this view of the neural code is correct, even if neurophysiologists were to measure only action potentials for an eternity, neuroscience would never truly crack the neuronal code. Doing so would be like trying to decipher what someone is saying by observing air vibrations as they come off the vocal cords without observing how the mouth is formed or how the mouth filters vibrations in highly specific ways. Measuring only the vibrations of the vocal cords would yield something like this. On the other hand, measuring only the filtering of the mouth in the absence of the energy passed through the filter of the mouth would yield this. So we need both energy passing through the system and filtering of that energy into words in order to realize information. We need both the yang and the yin of the neural code. Without both action potentials and rapid synaptic reweighting, we would not be able to realize information or mental events in neural activity. Let me repeat, we need both action potentials and we need the filtering realized in dynamic and rapidly resetting synaptic weights. The analogy can be taken even further in the sense that the shape of the mouth has to be formed before the air is passed through the mouth. Similarly, criteria for firing have to be set on a postsynaptic neuron before the arrival of presynaptic action potentials will be able to make it fire as a result of meeting the informational criteria realized in its physical criteria for firing. Indeed, the mouth must be shaped dynamically on a continual basis in order for the mouth to be able to speak. Action potentials are therefore a necessary but not sufficient basis for neural information processing whereby neurons convey information or talk to each other. The current dominant bias in neuroscience that the neural code is ultimately an action potential code is misguided. Action potentials are only half the story. The other half of the story is synaptic reweighting. Another current confusion in neuroscience is to think that one can understand how neurons communicate with one another if one understands how neurons are statically connected to one another via axons. The field of connectomics aims to map out exactly how every neuron is connected to every other. But let's say I had a perfect understanding of the highway system of the United States. That would not be enough for me to understand patterns of traffic in America. It might help somewhat in that I can guess that 2 points connected by bigger highways likely share more traffic between them, but just knowing the highway system will not help me understand the dynamics of traffic across the highway system, and it would definitely not help me understand why one car follows the path that it does. So if connectomics is rooted in a metaphor of the brain as a highway, I would have to conclude that this is a pretty poor metaphor. Maybe we need a better metaphor. Maybe the brain is less like a highway system of axons and more like a train track system where axons play the role of train tracks and synapses play the role of those shunts that shift trains from one track to another. If synapses are conceived of as switches that can be turned on and off, then perhaps the majority of synapses might be off at any given time, as in the simple cell example I gave at the end of the previous section. But when needed, switches could be turned on. This permits the possibility of sculpting neuronal epicircuits on the fly to construct neural circuits that are needed at a given time, rather like switching the railroad switches on train tracks to create different track connections as needed. Think about a segment of railroad tracks. Depending on how the switches are set, a single stretch of railroad tracks, say in Ohio, can be part of an epi-track that links Boston to San Diego, or Boston to Vancouver, or New York City to Mexico, and so on. The metaphor of the brain as a train track system, however, breaks down because synaptic weights, in the case of neurons, need not be limited to the black and white case of on or off, or this way or that way, as is the case in binary train track switches or light switches. Synaptic weights can generally be modulated up and down like dimmer switches. Criterial causality does not require that a response be all or none like an action potential. Criteria can be physically realized such that they can be met to degrees or not, amounting to fuzzy or hard thresholds for criterial satisfaction. As I've said before, metaphors are useful in helping us understand something that we don't understand in terms of something that we do understand, but if taken too far, lead to confusion. At the end of the day, when it comes to the brain and the mind realized in it, I think all metaphors will fail if taken too far, for the simple reason that there's nothing in the non-biological universe that operates like a brain, especially a human brain.